Okay, welcome back, boys and girls. This is the last lesson from Chapter 5. This is going to be the trapezoidal rule. So we're going to be dealing with trapezoids and something called Simpsons Rule. So two little rules here. You're going to feel that we're kind of going backwards, and we kind of are. Just kind of follow the textbook here. So the trapezoidal rule is actually another approximation method. So the approximation method that we have dealt with already, you remember LRAM, RRAM, and IMRAM. We just went over these. The problem is with the R's that you have here, the second set of R's, this R, and this R are all the same word, and the same word here being rectangles. Rectangular. Okay, and if you think about taking a function and creating a whole bunch of rectangles, you start to notice that there's a lot of wasted space. So there's a lot of over approximating and under approximating, and that's why it's an approximation method. You're never going to get exact, but the smaller your intervals, the closer your rectangles are going to be to an exact value. Now, here's the thing. What if we weren't to use rectangles? What if we were to use trapezoids? So you have your curve here, whatever it may be, and you go up and you touch, and you go up and you touch, and then you create the line between those, and you go up, you touch, you go up, you touch, you create the line between those. You still get a little bit of an over or under approximation, but you might see that this actually gets a lot closer to the curve itself. So this is what the trapezoidal rule is going to be dealing with. Now, we have actually done this already, you just don't know it. And the reason is the trapezoidal rule ends up being the numerical average of LRAM and IMRAM. And we did this already. We did this in pre-calculus. We said, okay, the IMRAM and the LRAM, if we add those two things together and divide by 2, we get a closer approximation. Well, that ends up being the trapezoidal rule, adding them up and dividing by 2, sort of. But we actually have a rule for using just trapezoids. Rather than looking at LRAM and IMRAM, rather than doing LRAM and IMRAM, we're going to use trapezoids. And there's a very, I'm going to say simple, but it's not going to look simple, formula in order to do this. And I'm going to show you this here, but then I'm going to show you on the next page where this comes from. All right, so if we want to approximate this function, the interval or the integral of this function from a to b, we could say, okay, t being trapezoid area, it's going to be equal to, or the area is going to be approximately equal to h over 2 times y sub 0 plus 2y sub 1 plus 2y sub 2 plus blah, 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 all the way out to y sub n. And these y sub zeros, this would be on your function right here, this height would be y sub 0. The next height would be y sub 1. The next height would be y sub 2 because they're y values, right? That's the height. And then h, if you remember trapezoids, h is going to be this distance here on the x-axis. So it's going to be taking the interval from b to a and cutting it in half, or the distance between b and a, and divided by 2. Oops, I'm sorry. That is not 2. I was going to say, that didn't look right. This is, re-scratch that, b minus a over n. I don't know where the 2 came from because that didn't make sense. It has to be over the number of intervals that you're doing. All right, so h is equal to b minus a over n. Now, you may not be seeing why this particular equation comes out. H over 2 times this big long sum. Well, you can kind of think about the fact that we're summing a whole bunch of trapezoids, and the h over 2 kind of makes sense because there's an h over 2 in the trapezoid area problem, right? It's h over 2 times base 1 plus base 2. So let's take a look at what this would look like. Where did that thing come from? Thinking about a function here, if I just created an xy axis and I just created some random function here, I kind of like the bell curve for no reason. Going from a to b, you'd be thinking about a bunch of trapezoids here. And trapezoid comes up, and it comes up and creates the trapezoid here. It's going to go up. It's going to create the trapezoid there. It's going to go up, create the trapezoid, and you get the idea. Well, this is y sub 1, as I was mentioning, or sorry, y sub 0. This is y sub 1, the height. Remember, we're talking about the height here, or the base of the trapezoid, really. Y sub 2, y sub 3, and so on and so forth down to y sub n, where we would look at this, where this would be y sub n, and this one before it would be y sub n minus 1, the one before the last one. All right, so thinking about the area of all of these trapezoids, if we write it a little bit different, so you might know that area of a trapezoid is h over 2 times base 1 plus base 2. But it's also equal to a slightly different formula where it says h times b1 plus b2 all over 2. So I'm adding up a whole bunch of these trapezoids, or this looking trapezoid. So I could say it's actually h times, well, base 1, that would be the height here. That would be y sub 0. Y sub 0 plus y sub 1. That would be my first trapezoid, right? Y sub 0 plus y sub 1 over 2. I'm going to add the next trapezoid. So the next trapezoid would be, oh, look, notice I'm going to reuse the y sub 1 plus y sub 2 over 2 plus so on and so forth all the way down to y sub n minus 1 plus y sub n all over 2. Now here's what's interesting. If you were to split these fractions up, this would be y sub 0 over 2 plus y sub 1 over 2 plus y sub 1 over 2. Well, that's pretty interesting. Plus y sub 2 over 2 plus y sub 2 over 2. And this continues all the way down to the last one. And the last one here, you would end up with just a y sub n over 2. Notice that this n minus 1 would be paired up with another n minus 1. Well, you might be seeing this now. If I took h times y sub 0 over 2, I would actually end up with, well, here, if I have half of something and add another half of something, I'm just going to get the full thing. Plus dot, 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 all the way out to y sub n. Oops, sorry, y sub n over 2. Okay, so, well, then how did I get the formula from before? Well, I don't really like fractions in here, so I'm going to factor out a half. And if I factor out a half out of a 1, I get 2, because you got to think about distributing that. And notice this now gets that pretty kind of ugly looking formula, but it's actually pretty useful, right? Formulas are always nice. And what I can do here is you might want to pause here because I'm going to erase all this stuff if you haven't written it all down yet. But I want to think about, what if I gave you an example? What if I said, hey, let's find from 0 to 2 of x squared dx. Now I know you guys can find the antiderivative and do some calculations here, but let's think about the trapezoidal rule here. Let's break it up into, let's say n equals 4. Let's break it up into 4 intervals. So on your graph, you would go 0 to 2, and you basically be going by halves. I kind of like doing halves. All right, so I can think about using the trapezoidal rule here. I can say h. Well, h is basically the length of these intervals. So the length is half over 2, because that's my formula, times y sub 1. Well, y sub 1 is going to be 0. Plus 2 times the height of the second number here. And since that's a half, half squared is 1/4. Plus 2 times y sub 3 in this, or sorry, y sub 2 in this case, which is the next one. So this is, by the way, y sub 0, y sub 1, y sub 2, y sub 3, and y sub 4. So we keep going like this. This is a 1, so it's going to come out 1 squared is 1 plus 2 times, that's 3 halves, so it becomes 9/4, plus a 4. So you remember the beginning and the end doesn't have the 2 on it. So this is 1/4 times 0 plus 1/2 plus 2 plus 9/2 plus 4 is 1/4 times 6. Oh, that's 5, so 11. So it's 11/4. Is that even close? You could figure that out for yourself. Is that close to the exact thing? You could figure out the exact answer without really much difficulty anymore, I think, for x squared. But that's where this trapezoidal rule is going to come in handy. And actually, it comes in handy when you're doing a discrete data. So discrete data being things like a table. So you'll see in the text on page 308, it talks about average temperatures. And average temperature is, you could make a fluid graph, but it's actually called discrete data because we're starting with 1 hour. Let's say at noon. I think in this particular example, you're talking about every hour after noon. So noon, it's 63. At 1 o'clock, it's 65. At 2 o'clock, it's 66. At 3 o'clock, it's 68. And so on and so forth out to midnight, where it's 55 degrees. And you could actually figure out what they're actually asking is the average value. Well, average value is given by 1 over b minus a from a to b of f of x dx. Well, the problem with doing the discrete data is you don't actually have a function to deal with. Now, some of you are going to try to create some random function on your calculator that you're going to say, oh, this calculator says I can do this, but it's not how we want to do this. We want to think about this as a trapezoidal problem. Well, in this particular case, we're going from 0 to 12. So I could say, okay, it's 1 over 12 minus 0, right? Because 0 being the first hour or the noon and then 12 hours away, right? So 0 to 12 of f of x dx. Well, it just so happens you could figure out this integral by using trapezoidal rule, where these are all of your y sub n's. And the distance between these two things is all of your h's. So you notice the h is always 1 in this case. Actually comes out to be a pretty simple problem once you think about the trapezoidal rule, but it becomes more complicated if you try to create a function that you could then integrate. All right, so discrete data, actually, it's just dawning on me now that the trapezoidal rule works a lot better here for discrete data than it does for an actual function, since we know how to integrate functions by now. Okay, so I think I've pressured this one enough. Let's go ahead and look at Simpsons Rule. Well, it just so happens that Simpsons Rule is another approximation method. And you're probably asking yourself why, and you know what? So was I. And it just so happens you do a little bit of reading in the textbook, and I do that every once in a while. I have to make sure I understand what they're talking about. All right, so a lot of these rules, these approximation methods, are actually used in computer calculations. So somebody creates this approximation method, and then they use it in a computer, and it even says in the book sometimes some people won't even tell you what their approximation method is because they're thinking it's like a copywritten thing. They created the method, and it might be. But in this particular case, this is one of those ancient rules that came along long before this guy named Simpson came along. Kind of like the Pythagorean theorem. Pythagoras didn't invent it. People were using that thousands of years before he was. And this is the same kind of case. And I was reading the text. They're like, hey, this guy actually all he did was he referenced this method in a textbook that he wrote, and then he got his name on it. So apparently that's how you get your name famous. You write a textbook using a method that's not been named, and it will be named after you. Okay? But you got to be good at what you're doing. You can't just try to write a book. All right, so that being said, let's see what this is going to look like. This is going to look a lot very similar to the trapezoidal rule. This one I'm not going to do the whole method of breaking things up for you. I'm just going to give this to you. In order to approximate this integral from a to b, s being a Simpsons approximation here, or Simpsons Rule approximation, it's going to be h divided by 3. And you'll notice the formula looks a little bit the same, but quite a bit different, right? We got 4s and 2s, 4s and 2s, 4 and 2, 4 and 2, 4, 2, 4, 2, 4. And the 4, 2 alternates like this the whole time. So the next one here would be 2 y sub 4, 4 y sub 5, that sort of idea. Now here's where this one changes. In a trapezoidal rule, you can break it up into any number of intervals that you want. However, in Simpsons Rule, you need to partition it into an even number of sub-intervals. An even number. So you can't do this with a 3. You can't break this into 3 sub-intervals. All right, so that being said, we have this nice long formula here. Same idea, and what ends up being is this particular rule actually approximates a little bit closer to, it's actually a little bit better approximation than trapezoidal rule. It's going to be one of those things where you're going to need to just know the two rules in order to answer the questions that are based on those two rules. So if I said use the trapezoidal rule to find the area, or use Simpsons rule to find the area. And you'll see those in the textbook here. All right, so the other piece to this that goes along with this is you want to kind of know how close of an approximation did I get. And so we have two little error calculations, and they're going to look kind of ugly. And I'm kind of using that word loosely here. Not ugly in the sense that they're super big, but ugly in the sense that there's a lot of variables. All right, so we know that these are approximations, so you know there's some sort of error according to the actual area. So if you're using the trapezoidal rule, we can find the error. Basically like percent error, right? So like percent error is something we've done before where it's, how do we do this? We'd say new minus old over old, basically, and then times by 100 to get a percent. Percent change from 5 to 3 would be 3 minus 5 over, what we started with was 5. So it would be a 40% decrease, that sort of idea. Now, this particular method is, the absolute value bars are just there to show that it's always a positive number, so don't worry too much about this. But it's the integral from b to a, so we're still looking at the integral from a to b, sorry, I didn't say a to b, of f of x dx, and if you're looking at the trapezoidal rule, it's going to be b minus a over 12. The 12 is a given number, it's always 12 in this case, times h squared, where h is that distance, and h, remember, is h equals b minus a over n. So that's pretty easy. And then this part here is the kind of interesting looking thing. This is going to be the max value of f double prime. Oh, we're going back to derivatives. That sounds like fun. So you got to find the maximum of f double prime. Or the second derivative, the max of the second derivative of the original function that's inside the integral. All right, and then if you were to use Simpsons rule, this is a slightly different slightly different error formula. This is just error sub s, e sub s, and it's still b minus a, but in this case it's over 180 times h to the fourth power times max value of f to the fourth. No, it's not f to the fourth. That is actually the fourth derivative. And if you've been paying attention, you can take the derivative infinitely many times. And you can find the fourth derivative, and you can find the maximum of that. Okay, these are actually pretty straightforward formulas that you can use. I think I only ask you on, I could be lying because sometimes I miss a problem, but I think I'm only asking you one, and I think you're going to be asked to do this particular one, the Simpsons approximation here, the Simpsons error approximation. Um, but that's it. That's the end of chapter 5. I hope you've enjoyed it. We will get deeper and deeper into our anti-differentiation, and we actually have a whole bunch of rules that we get to deal with, just like derivatives. So I hope you have enjoyed chapter 5 so far, and I will see you guys in the morning tomorrow.